Hey, thanks so much for watching. We have so many more programs, so don't forget to subscribe. Hey everyone, thanks for joining us. We haven't done one of these live stream Q&As in a while, and I always enjoy them. I hope that you enjoy them as well. Feel free to put your question in the chat, and I'll try to get to as many as I can. We've also gathered some of your questions that you submitted earlier today on Facebook, Instagram, X, and so forth. So I'll try to get to as many of those as I can. Today is, of course, an interesting news day. We have the Artemis mission, which is going to be splashing down safely. We have our fingers crossed, hopes and prayers that that will go smoothly. It launched, I guess, on April 1st. I think we have even a little bit of footage of that we can show you here. So there it is, taking off, heading on its 10-day mission, which concludes today. I believe the splashdown is 8:07 Eastern time, but this will be off of the coast of California near San Diego. You see the crew there before they were, yes, they were already in space as well. And, you know, they've done some wonderful things. We've gotten these beautiful images of the Earth from space. We've seen those before, but these are sharp, stunning, absolutely beautiful. They've taken a variety of photographs as well from a vantage point that is deeply unfamiliar. There you see the Earth setting behind the cratered moon, which is really just so stunning, so beautiful. They also, here's another version of that where you sort of see the Earth. I think they called it Earth set, you know, the Earth setting behind the moon. They also had a beautiful photograph taken of the silhouette of the moon with the sun in the background. So we here have a version of a solar eclipse, but at a vantage point that is deeply unfamiliar. And I think this version of totality, if I'm not mistaken, was 57 minutes long because the crew was so close to the moon. So it's sort of a beautiful image where you sort of see the sun linking out there behind the edge of the lunar landscape. And so this is a wonderful mission that, you know, we've not been to the moon now for 54 years. We, of course, went back in the 60s with the Kennedy goal of getting us to the moon in a decade. We got there, and then we kind of gave up a little bit, but this is the start of a new era, which is really wonderful and exciting. And look, you know, I think you've probably read more about it than I have. There are these potential issues with the heat shield. You hear that, and of course your heart sinks. Certainly if you're my age, you remember the previous disasters with a kind of visceral reaction. But we're told that NASA has a wide margin of error here, so everything should go well with that. So let me, with that, get to the main point of our gathering here today, which is to address some of your questions. And I see there's one immediately to do with Artemis. So could Artemis II and future missions help test fundamental physics like quantum gravity, information preservation, or general relativity deviations during lunar flybys? What insight do you hope Artemis will bring? Look, we don't really look, if there were some measurement that gave us some insight into quantum gravity, we would be over the moon, to use perhaps an apt phrase for this particular context. But that's not why the Artemis mission exists. The issues with quantum gravity emerge in extreme realms that are extraordinarily energetic, extraordinarily small, the kind of gravitational influence that's relevant for Artemis, Isaac Newton could have done the calculations. And in fact, for the most part, Isaac Newton does do the calculations for us even today, because Newtonian gravity, even though we've gone beyond it with Einsteinian gravity, general relativity, and even though we're trying to push the frontiers with quantum gravity, for everyday situations, by which I mean situations that are amenable to the naked eye. If you can sort of see things, you can see the moon, you can see the Artemis spacecraft itself, that's your big hint that ordinary Newtonian gravity is all that you need. So, yeah, is there always a chance that some kind of anomaly that we didn't expect crops up and somehow we gain insight that we didn't deserve? We weren't expecting it. Is that possible? It is. But I don't think that that is likely to be in the cards for us at all. Another question. Given that a single photon has energy and momentum, is it theoretically possible to create a black hole by concentrating energy through light into a single point? The answer to that is absolutely yes, right? So we talk about black holes in rough language by the idea of taking a ball of matter, often thought about as a star, but it could be anything, and crushing that mass to a sufficiently small size. And Einstein even gave us a formula for how small you have to squeeze a mass to get a black hole, right? And it's 2 times Newton's constant g times the mass divided by c squared. And so that's the canonical way that we think about black holes forming. But the reality is, both in special relativity and general relativity, Einstein is emphasizing that matter is one special kind of a more general concept called energy, right? And so all you need is energy to create a black hole. Energy is what sources gravity. And so photons, radiation more generally, they have energy. And so, yeah, if you get enough of that energy in a small enough region, you can create a black hole. In fact, this very same formula applies. Now just using E equals mc squared, just plug that in. And so you need E to be the dominant entity that is sourcing the gravity, as opposed to M, which is what we normally think about in the canonical way of thinking about things. But if you squeeze it to 2GE over C to the fourth, you C to the fourth now because of E equals mc squared, you can just go through it, then yeah, you will have a black hole made of light, right? It's kind of a cool idea, right? A black hole that forms from photons being sufficiently concentrated in a small enough region. If the universe were in absolute stasis, would time still have meaning? Is time an independent reality, or is it entirely dependent on change and perception? So maybe I'll give some names of people who ask these questions. That's Mensurth Artha 4374. So, it's a tough question. We don't really know fundamentally what time is. We don't know if time is something that we somehow impose on some external reality to organize our perceptions in order to have some sense of causality, of a cause and an effect, and things of that nature. So, without a deep understanding of what time is, it's difficult to answer that question. But from a practical sense, I would say absolutely, because time is what allows for change, right? That's the role that time plays in fundamental physics. And so if you're telling me that there are fundamentally no change, there's fundamentally an absence of change, that we're fundamentally in a realm of complete stasis, then the role of time would drop out, right? I mean, even to have a thought, there has to be change happening inside of your head. And so if everything is frozen, if it's total stasis, from any practical standpoint, a notion of time completely drops away. Okay, if space is inflating, asks Scott Tate 4968. If space is inflating, why isn't the space around us and between us inflating too? That's a good question. And here's the answer. When we're talking about the expansion of space, the driver of that is the gravitational force. In Einstein's theory, in the original version, without using this more exotic idea of inflation that you make use of, it's the very fact that space can stretch or it can contract, and it is matter and energy that sources those changes in size. And that's the origin of an expanding universe. Inflation, it's the same basic idea. It's just the source of the gravitational force is a little different. It's a uniform energy as opposed to clumpy chunks of matter. And uniform energy, it turns out, in Einstein's equations, gives rise to a repulsive gravity that pushes everything apart. But it's gravity that is driving the change. And so if you're in a realm like we are right here, say our bodies, just to be concrete, our bodies are held together by non-gravitational forces that are stronger than the gravitational forces. Our bodies are held together by the electromagnetic forces, by the strong and weak nuclear forces that are operating within the nuclei of the atoms and the molecules that make up our bodies. And because those forces are so much more powerful than the force of gravity, our bodies and the world around us is able to hold together and not succumb to the expansion of space. That's the answer to your question. But just to take it a little bit further, there are people who have studied theories, which are slight generalizations of the, say, inflationary theory that you make reference to, in which the strength of the gravitational force, and more specifically, the strength of the repulsive push that's driving the universe to still be in a state of accelerated expansion, that force grows more strongly over time. Given that, there's a chance that today that force is much weaker than the forces that hold things together. But over time, if it gets stronger, maybe it gets stronger than the forces that hold matter together. And if that's the case, then in the far future, the answer to your question will be different. We will expand from the gravitational force that's driving everything apart. Even individual atoms, the electrons, may find themselves ripped away from the nucleus because the little space between them is allowing for expansion that's stronger than the electromagnetic interaction that's keeping that electron in orbit. This is known as the Big Rip. It's one way that, in principle, the universe might end. And if it does, well, that won't be that pleasant, but we're talking about timescales that are way, way off into the future, so you don't have to worry about it. But that's the answer to your question. If time has a beginning and an end, how would that affect multiple universes? Would different universes be on the same timeline as us? And this is coming from Crankin 72. Yeah. So if there are other universes, that's a big supposition, and there are no doubt going to be other questions along the lines, as this is a fan favorite topic. But if our universe is just one among many universes, then the language that we've long used, that time in some practical sense came into existence with the Big Bang. That notion of time, of course, is only relevant to our Big Bang, our universe. If there are multiple Big Bangs, say, giving rise to universes at distinct locations in some larger multiverse reality, then time in each of those universes would have come into existence in the same sense with the Big Bang that drove the expansion of space in that universe. And so, yes, the concept of time as we normally use it would become a local description. It would be relevant to the reality that we inhabit, but it wouldn't be talking about the reality in those other universes. Now, you can still ask the question, does that mean that there might be some more universal, some overall notion of time that would kind of apply to the entirety of the multiverse? And that's pretty tough to work out in any way that makes sense, because one of the insights of Einstein in general relativity is that the flow of time, although he didn't really use that language, but the rate at which time elapses is influenced by the conditions, by the matter and energy in some region of this larger reality. And so time here can be very different from time over there, even in our universe, right? Time near a black hole, very different from the time that I'm experiencing right here. Now, if I was at the edge of a black hole, I wouldn't feel time behaving strangely because everything about time would be affected uniformly. Even my thoughts would be affected. In fact, they would be slowed down relative to the thoughts that I'm having right here, far away. But it's only by comparison with your friend back on Earth that you'd recognize that time for you elapsed in a strange way. But the point is, this urge that we have to have a universal conception of time that applies to everything is misguided. The reason why it has a partial home in our universe is the fact that on the largest of scales, our universe is pretty homogeneous. So, yeah, if you look in the vicinity of the solar system, Milky Way galaxy, you see like a lot of matter. And then in other regions, there's mostly empty space. But if you look at a large chunk of our universe, whatever, 100 billion light year box on each side, and you look at the conditions in that box compared to the conditions in another such enormous box that's someplace else in the universe, the conditions are pretty much the same. And because of that large scale homogeneity, there is a large scale notion of time that we can pretty much invoke. And that's the one that we are using when we say that the universe is whatever, 13.82 billion years old. You could easily have said 13.8 billion years according to who? According to whose clock, right? Because clocks tick off time at different rates. Answer: we're talking about time on a clock that's moving with the general expansion of the universe and experiencing the average conditions of matter and energy spread throughout the universe that are pretty much uniform. And that's the clock that we have in mind. But if we lived in a universe that was heterogeneous completely, there was no large scale uniformity, then there really would be no notion of some large scale overall universal conception of time. All right, I know this is off the wall, but can an entangled particle be both inside and outside of a black hole, resulting in gaining an ability to somehow monitor the one inside by how the one outside is acting? And this is from MRX 1278. That's not off the wall. MRX, you are putting your finger on one of the most contentious and interesting and fruitful debates that physicists at the leading edge have been having over the last, let's call it, well, you could call it 25 years, but over the last decade for sure. So what's the idea? The point that you raised, just to bring everybody onto the same page, if you have a black hole, right? And you have an entangled pair of particles. Remember from quantum mechanics, that's the idea that you can have two particles that are each in a superposition, let's say, of being spinning up and spinning down. So in a 50-50 mixture here, and then a 50-50 mixture here. And yet when you measure one and it snaps out of the haze and points up, the other one snaps out of the haze and points down. Regardless of how far apart they are, they behave, therefore, as if they're right next to each other. They have this tightly choreographed way of behaving that makes it appear that they're linked even though they're far apart. So then MRX suggests, well, what if you do that, entangled particles, with one outside a black hole and one inside a black hole? Then aren't you learning about a part of the universe that you're supposedly unable to access by virtue of the entangled partner on the other side? And the most conventional answer from general relativity is yes, right? So if you measure that entangled member on the outside and it's spinning up, then you will have learned that the one on the inside is spinning down. Now, that doesn't actually violate any insights. What black holes really stipulate, and they're defined by, is a better way of saying it, is that a light beam can't escape. Nothing can escape. When you do this, nothing's escaping. You're learning about something inside the black hole, but you're doing it through this beautiful indirect quality of entanglement that quantum mechanics provides. But the real issue that people have argued about has to do with Hawking radiation that you may have heard of, which is this idea that when you have a black hole, It can cause, and we believe it will cause, according to Stephen Hawking, radiation from quantum physics to bubble up at the surface and stream away. Number one, that's weird. That means black holes are not completely black. This is an idea that Hawking introduced to the world in 1974. So, whatever, more than 50 years ago. But there are puzzles associated with that because when particles bubble up near the edge of a black hole, near the event horizon, they are entangled, just as MRX has asked us about. And so when one member of the pair flies away, its partner flies in, and they are entangled, exactly as in the question. And so people have wondered about the issue of, can they carry away the information of whatever fell in to create the black hole? Or is that radiation somehow in a thermal state that doesn't carry any information? This has been the issue that people have been debating for some time, and it all fixates on exactly the question you asked. So, according to standard general relativity, yes, particle inside, outside, still entangled. But according to some more wild ideas that the debate has inspired, some suggest that maybe the event horizon of a black hole severs the entangled relationship between those two particles. They're no longer entangled because of that. And moreover, sort of like when you snap a rubber band, you release energy. If you snap entanglement, you also release energy, which means that the surrounding region of a black hole, the event horizon, would be highly energetic. So energetic that anything that gets too close, falls in, would be incinerated. And so it's not that something falls into the black hole in this new picture. Rather, it's that the black hole sort of the end. You can't go any further. It's called a firewall. And so people have been debating this idea for some time. All right. What do we have here? Could the fundamental constants be different in other universes? Dave Mart asks this question. And yeah, absolutely. So we're used to certain fundamental constants of nature. You learned some of them in high school. You learned about things like the speed of light. You learned about Newton's gravitational constant. You learned about the electric charge on an electron and various other particular numbers that seem vital to characterizing physics in our universe. When we study the possibility of other universes, depending on exactly how those other universes are formed, there are examples of the multiverse in which the other universes could have different values for the electric charge, different values for the mass of the electron, different values for the speed of light. In fact, you can imagine universes where there's no notion of the speed of light because there's no notion of light in that universe. And so, depending on how far you're willing to go in the mechanism by which other universes are created, you can have more or less latitude in the values of these fundamental constants. And so, yes, people have wondered about the possibility that maybe, just maybe, what happens is the following. In most of these other universes, the fundamental constants of nature in those realms are such that the kinds of structures necessary for living systems, a stable planet, stable stars, certain biomolecules, at least life as we know it, that give rise to amino acids, that give rise to the nucleotides of DNA and so forth. Maybe in the vast majority of those other universes, those structures can't form because the constants of nature are different. And with those particular values, you don't get the kind of material structures that life as we know it requires. And that might give you an explanation for why we're in this particular universe with this particular value of the electric charge and the mass of the electron and the mass of the quarks and the strength of gravity and the strength of the electromagnetic force. Those are puzzles. Why those particular numbers? Potential answer, maybe if the numbers were significantly different, we couldn't live. We couldn't exist. Life as we know it wouldn't form. So, why are we in a universe with the particular values of the constants that we observe? Because this is the only kind of universe in which we could exist. This is known as the anthropic principle, and some people find it repellent. The reason they find it repellent is they say we should not be part of the fundamental explanation for anything. We are just the outcome of the universe that we inhabit. We're the kind of afterthought. The fundamental issues of why the universe is the way it is should not depend upon us. But think about it. I mean, I get it. I have a certain sympathy for that way of talking about things. But if there are other universes in which these numbers that puzzle us have different values, and maybe all possible values are realized across the grand expanse of the multiverse, then the nature of the question shifts. It's not why does the electron have its particular charge or its particular mass, because it doesn't. In other universes, it has different values. Then the question is instead, why are we in a universe with the particular values that we happen to measure? And the answer may well be we simply couldn't exist in any of the other universes. And so you have to, I think, leave yourself open to this way of thinking. If you can find a more fundamental explanation, God bless you. Write it up, publish it, go to Stockholm. Fantastic. But no one's been able to do that. And so in the absence of a fundamental explanation, it may be more of an environmental influence. We have to allow that as a possibility. Okay. How will humans and equipment on the moon for prolonged periods be protected from meteors or meteorites that regularly fall on it? This is Tony from Facebook. Well, I'm not much of an engineer, so I don't know if I know all the tricks of the trade, but certainly, well, look, you can imagine building a lunar base that's under the surface. That helps to protect you. But if you're on the surface, there are various things that you can do to mitigate the situation of being obliterated by a meteorite. Now, one among them is to first recognize that there's more of an issue on the moon than there is on, say, the Earth. The Earth has an atmosphere. And so many of the smaller meteorites, they just burn up in the atmosphere, or they're at least slowed down and they burn up. And what's left, the remnant, is much smaller than what began at the top of the atmosphere, making it much less dangerous. And so what you want to do on the moon, since you don't have an atmosphere, is you want to put something above sensitive areas that will protect you. Now, how do you do that? It's pretty tough to have some hardened structure that can take the impact of a meteor that hasn't degraded by going through an atmosphere. So you want to degrade any incoming meteors. How do you do that? Well, mostly what people do is they imagine you have a series of shields, okay? And when the meteor hits the first shield, you're not trying to stop it. Rather, you're trying to cause it to pulverize so that the material is spread over a larger area. Larger area means less force per unit area. And then you can have layer upon layer upon layer of these shields. And the layers don't have to do as much work as you would have thought because the meteor was caused to disintegrate upon impact on the first shield. I think there's a strange name for this design. I can't remember. I think don't quote me on this. I think it's called the Whipple shield. I don't know. Somebody look it up and tell me if that's correct in the comments. But I think that is the basic idea for protecting surface material on a body like the moon that doesn't have an atmosphere. Okay, next question. Jesus, what is this one? From Ideas QFAJIT. If I had a device to do live FaceTime using quantum entanglement, let's say we have one. Okay, this is a little tricky for me to picture. One person near a black hole event horizon and one on Earth talking to each other. What do they see? Okay, I don't know if quantum entanglement is so essential to what you're saying. I think you're basically saying, if somehow we can have a FaceTime call with someone on the edge of a black hole, sort of what would you see? Well, the dominant thing that you'd notice is that your companion near the edge of the black hole would be in slow motion compared to you because one of the deep insights of general relativity that I don't think has fully spread throughout even the scientifically savvy part of our world, which is distressingly smaller than we would like it to be, is that what Einstein really showed with general relativity is that you can think about gravity, at least in the familiar context, like the Earth or even a black hole. You can think of gravity as that which slows the passage of time, especially near an ordinary body like the Earth. That is the dominant way in which gravity manifests itself, according to Einstein. We often say that the Earth curves the environment around it. You've seen these images. I've used them myself all the time. The sun causes the fabric of space to curve, and then the Earth goes in orbit around the sun because it's traversing a valley in the warped spatial environment. Between us, since we're, all here in good faith and friends, that's really misleading. If you look a little bit more closely in general relativity, what really happens is not that space is warped near the sun or near the Earth, it's time that's warped. In any sensible way of describing it, you can always change coordinates, but any sensible way of describing it, it's time that's warped. And so the reason why an object falls when you drop it is not that it's sliding along an indentation in space, which is easier to visualize, but rather an object falls because, if you don't jump on me for using unnecessarily anthropomorphic language, the object wants to go to a region of space where time elapses more slowly. And time elapses more slowly near the surface of a body because you're closer to the source of gravity. Gravity pulls on time, slows its passage. Now, if you're near a black hole, back to your question, well, the gravitational pull there is strong. And so your friend, your companion near the black hole will be talking in slow motion and moving in slow motion, eyes blinking in slow motion. You'd also note that they are redshifted because the light that they are emitted is fighting to get out of the gravitational field of the black hole. And when you fight against a gravitational field and you are an oscillating electromagnetic field, the field gets kind of stretched out. The wavelength becomes longer, and that pushes it toward the red end of the spectrum. Those are the kinds of things that you would see. In quantum entanglement, Abby Doodle 2458 asks, in quantum entanglement, do the results when you affect one of the atoms always have to be opposite each other? Is a way to determine what the pair is and outcomes, whether they're the same or opposite. And Abby Doodle, thank you for asking that, because again, I'm guilty of it too. We can get caught in our ways of popularizing these unfamiliar ideas, and certainly using spin of a particle like an electron is a very familiar one. And indeed, even a moment ago, I said, if this one is pointing up, this one's pointing down, and vice versa when you undertake a measurement. But Abby, you're completely right. That's merely one example. Even with electron spins, I could set it up in a different quantum state where they're both up or they're both down. So now it's more like this. They can be in a 50-50 mixture of spinning up and spinning down. And when I measure one, it snaps out of the haze and spins up, and the other snaps out of the haze and spins up too. It's not so much opposite or the same, it's rather the choreography is rigid. And so how do you figure out whether it's opposite, the same, or something even more exotic? That's where you have to look at the details of the quantum mechanical configuration itself. Any undergraduate who takes a basic course in quantum mechanics will learn how to represent the quantum mechanical states mathematically. And then it's a tiny little exercise to figure out what the quantum mechanical state looks like, so that two electron spins are like this or like that, or something far more involved than electron spins. It could even be the positions of a particle. In fact, I should say, when Albert Einstein wrote the first paper on quantum entanglement, this is in 1935, he wrote it with two colleagues, Podolsky and Rosen. The word electron spin is not in that paper. They weren't using this or this as their example. That came from someone named David Bohm years later. Rather, when Einstein wrote down quantum entanglement, he did it in terms of more familiar qualities, position. He set up things mathematically so that the position of one particle was entangled with the position of another particle. When one particle is found here, this one's found here. If this one's found here, this one's found there. A very precise relationship between their locations. And so, yes, Abby, it's a great question. And indeed, it is not that things are always same or opposite, is that they are tightly correlated. That is the best way of describing it. Okay. Dr. Greene, about the possible big rip. Yes, we did talk about that a moment ago. Gustavo, gust.av.o. Oh, hang on a second. It just moved on my screen. What would happen to the rest of the other dimensions from string theory? Would they be kept the same? What other thing could be expected to happen? Yeah, so it's a great question, Gustavo. You're making note of the fact that different dimensions of space, in principle, can expand or even contract in different ways. In fact, there are cosmological theories within string theory that does require extra dimensions where the three dimensions that we know about can be expanding, but the extra dimensions that we don't see with the naked eye, but the mathematics claims exist, those dimensions could be contracting while our dimensions are expanding. That wouldn't bother us because we don't see those extra dimensions, so we don't know what they're doing. We don't even know if they exist, of course, but assuming that they do, they could be static, maybe, or they could be contracting and they could be expanding. So, yes, can you imagine a situation where there's a big rip in our dimensions and not in the other ones? Yeah, yeah. It could be that the repulsive gravitational push within our three dimensions goes larger and larger and larger, but in the other dimensions, maybe the source of gravity that they are sensing is sufficiently different that they're undergoing different behavior. Absolutely possible. If energy is universal and dark matter forms stars and releases, will dark matter disappear? I'm having trouble grasping what the question there. Would dark matter disappear? Dark matter forms stars and releases. I'm not sure exactly what the question is, Rama. If you want to ask again, I'll try to come back to it, but I'm having trouble grasping that one. All right, Ignacio from Facebook. Since string theory attempts to unify gravity with quantum mechanics, how might precise measurements of gravitational fields during Artemis II inform such theories? Again, similar to before, not much I can say about Artemis II giving us deep insight into string theory or gravitational theory. Unfortunately, I wish that we could. Matteo Carazzi is one of our World Science Scholars. There's a program that we run at World Science Festival where math kids from around the world who are exceptionally talented are brought into our realm and learn from some of the great experts. In your view, Matteo asks, what would it take to rule out string theory conceptually? What kind of failure would make you conclude that the framework itself is fundamentally incomplete? Yeah, it's a great question. What would it take for me to give up on string theory? I wish I could sit here and say, in 5 years, there's going to be an experiment at such and such a collider, or in 10 years, there's going to be an observation by such and such space station or space observatory. And if it doesn't come out in a particular way, I'll give up on string theory. I can't say that. Nobody can. And the reason is, I think as many of you know, string theory has not yet developed to a point where we can make the kinds of definitive observational or experimental predictions that certainly we hoped we'd be able to do when I was a graduate student back in the 1980s. But in case you're interested, and maybe there are other questions, the achievements in other domains of string theory are so extraordinary that we are compelled to continue studying this theory. But just to answer Mateo's question, what would cause me to give up? Here's what would cause me to give up. If we find a mathematical inconsistency within the equations of string theory, if we find that there is an insoluble mathematical collision between the mathematical ingredients necessary for the theory to function, that's the point where we would be forced, any rational string theorists would be forced to say, ugh, we have to give this up. Now, I gave a little grimace here, and if I could roll back time, I would take that back, because my true feeling, and I'm really being serious here, my true feeling is if some young kid, I don't know, someone watching here in the next few years gets into string theory and finds that mathematical flaw, I would bow down to that esteemed researcher, because I don't care about string theory per se. I care about making progress toward truth. And so far as we can tell, string theory has all the makings to take us in the direction of truth. If, however, somebody were to find a fatal flaw in the equations, fantastic. We would throw string theory away at that point and gleefully, oh, that's perhaps too strong a word, move on to other ideas. We are nowhere near that place at the moment. Quite the contrary. Anybody who knows anything about the history of string theory knows that there have been mathematical miracle after mathematical miracle showing that the equations fit together in such a tight-knit manner with such graceful elegance that you are compelled to press on with a theory that for the first time puts together gravity and quantum mechanics. And so, yeah, that would be what it would take. A deep mathematical flaw, incommensurable, can't fix it, unsolvable, absolutely telling us that the mathematics is self-contradictory. That's the point where you absolutely give up. Instagram question: what aspect of quantum mechanics is fundamentally contradicting relativity? Is it just the collapse of the wave function or something more? I don't have a name here, but someone from Instagram. And no, it's definitely more, much, much more. So the collapse of the wave function is a real issue with quantum mechanics itself. In quantum mechanics, I think at least some of you in the audience know, you describe the external reality in terms of probabilities, probability of an electron being here or here or here. And then the question is, when you actually measure the electron, you always find it at one location or another. What happened to the other possibilities that seem to be inherent in the quantum mechanical description? And so people have talked about this idea of collapse of the wave function or collapse of the probability wave. When you measure the electron, you find it here, the wave collapses and all the probability comes together and spikes at the one location where you actually find the particle. The problem with that idea is that that spiking, that collapsing of the wave here and spiking here, contradicts the fundamental equation of quantum mechanics, the Schrodinger equation. And moreover, nobody has any idea how, whether, or if that actually happens. This is a deep problem with quantum mechanics itself, nothing to do with gravity, relativity. The problem with quantum mechanics and relativity is really different. And I would frame it in the following way. Einstein taught us that the geometry of space and time can curve, but the way in which the curvature occurs is very gentle. Even near a black hole, it's still relatively gentle curving of space and time, except at the center of a black hole. And the problem is when you bring quantum mechanics into the story, quantum mechanics is anything but gentle, right? Heisenberg and uncertainty tells us there's always a degree of fluctuation, a degree of uncertainty, a degree of fulmination, these jitters in the microscopic structure of the universe. And when you apply that to space, quantum mechanics and gravity, you need to bring quantum mechanics to bear in space, as space is what communicates gravity. Space itself begins to wildly fluctuate and undulate. And those undulations in space are so significant that Einstein's general relativity simply can't cope. That's really the heart of the conflict. And so string theory and other approaches, I'm not saying string theory is the only approach, have attempted to kind of quell those quantum jitters in the fabric of space. And that's the basic motivation for string theory, to put gravity and quantum mechanics together. I should say that in more recent times, our view has begun to shift. There are many who think of gravity as somehow, in some secret way, having quantum mechanics already embedded inside it. And rather, therefore, than trying to blend gravity and quantum mechanics, it's more trying to understand how to pull the quantum ideas out of gravity. You may have seen one of our programs with Raphael Busso. If you want to know more about that, you should check out that program. But he uses this nice language that gravity is kind of an oracle. Gravity knows more things than you would think it should. In fact, it knows some things about quantum mechanics. And so this is right at the forefront of ideas that we're developing. But that's really what the issue is, not just the collapse of the wave function. How can we know, ask TLM 9500, how can we know that the universe is 13 billion years old when we can't see more than a specific range? And you're right, we don't know that the universe writ large is 13.8 billion years old. We just know that in our realm, the part that we can see, the observable universe, very important to have the word observable in front. We see that the observable universe is stretching. We can see that, observations. And we can then use the understanding of how quickly it's expanding to basically wind the cosmic film in reverse. And in reverse, using mathematics, we can bring the universe smaller, smaller, smaller as we go back in time. And we can figure out how far back we have to wind the film, how far back in time we have to go for everything to be on top of everything else. And that is the 13.8 billion years. But you're right. Outside of the observable universe, there could be other universes. We discussed that a little while ago. There could be an infinite realm that is somehow fundamentally different from the realm that we have direct access to. It could have been around much longer. It could have been around infinitely long, for all that we know. So you're absolutely right. We can only talk about the part of the universe that we can directly see. Okay, Instagram question again. As AI and brain-computer interfaces blur the boundary between mind and machine, do you see the meaning of being human fundamentally changing or remaining continuous with what we are today? Well, look, of course, I have no more deep insight into this question than anybody. So it's really pure speculation, but that's what these sessions are for. And so here's my guess. Right now, we're in a period where it's a very much us and them attitude, right? You've got us humans, you've got the AI. For the most part, we're getting along pretty well. We make use of these AI systems in various ways to try to do things quicker, better, sharper, faster, and so forth. Even in science, AI is finding an increasingly broad footprint in research undertakings. Absolutely. All the same, there are those who are worried, and those worries are not misplaced. I don't share those worries deeply, but sure. I mean, there's definitely a concern that these AI systems may find a way to have their own desires, wishes, choices, the way they want things to be. And maybe that will be at odds with the things that we want. So then you get this us versus them. My suspicion is that over time, that's going to start to evaporate. I think we're going to find ourselves so deeply embedded within the AI world, and the AI world will find it so deeply embedded in our world that you won't be able to draw a sharp distinction between them. I'm not necessarily saying that whatever, we're going to plug these AI systems into our brains, and maybe we will, right? People are working on those sorts of things. But I just envision that we will go forward and there'll be some hybridization of some sort. Don't push me on the details. I can't really provide any. Some sort of hybridization where we are just this thing, which has both native intelligence and artificial intelligence, and it's just integrated together. And at that point, there's a chance that the us versus them goes away because we have, in some sense, evolved to a different configuration. Now, some people find that deeply distressing, to preserve our humanity. And look, I value humanity and our human nature as much as anybody, but I guess I'm open to the possibility that there could be a fruitful union that doesn't need to lead to disaster or to the elimination of the very things that we humans today consider to be our defining qualities. So maybe I'm too optimistic, but that's how I see that potentially going. AJ4RI, is there a connection between the expansion of space-time dark energy and the non-zero expectation value of the Higgs field? Wow, okay, that's a good question. So what is the Higgs field? The Higgs field, you remember from way back in 2012, it's this field that suffuses space. Finally, it was confirmed in 2012. July 4th was the announcement. And this field is what imparts mass to the elementary particles. The electron, for instance, as it tries to kind of, not a perfect analogy, but as it tries to plow through this Higgs field, it experiences a resistance. And that resistance is what you and I would refer to as the intrinsic mass of the electron. Dark energy is described using very similar language as the Higgs field. It doesn't impart mass to particles, but it's still a field, an energy that is spread throughout space. So the natural question is there a relationship between the Higgs field, which spreads energy through space, and the dark energy, which spreads energy through space? And in principle, there could be. People have certainly written papers trying to find connections between these two things. We believe that the energy in the Higgs field is sufficiently small that it doesn't give a major contribution to the expansion of space where the dark energy does. And that's sort of the main difference between them. But in more exotic theories, you don't just have one Higgs field. In some of the mathematics we write down, you can have multiple Higgs fields. And so could it be that one of those additional Higgs fields required by some of these other theories can have a tighter connection to the dark energy? Sure. And in fact, there are people who have studied the possibility that the dark energy might change in time. It may not have a fixed value for all time. And the way that you describe that mathematically is you use the field language for the dark energy. So that energy that's spread through space is carried by a field, and that field could have itself a dynamics where the value of the field is like slowly rolling down a hill, getting smaller and smaller over time, or getting bigger and bigger over time. It could go either direction. And so in that case, you'd be using exactly the same language of the Higgs field, the field language, as applied to the dark energy. So yes, there could be conceptually a profound connection between the two of these things. Lamb gratitude becoming. Oh, I am gratitude becoming. Sorry, my eyes are, the eye looks like an L. What do you think is the most beautiful feature of our universe? Most beautiful feature of our universe. Well, I think I would say the most beautiful feature is that it's comprehensible, which, as many before me have noted, is absolutely wondrous. Right? We we take it for granted that when we study a part of the universe, even the entire universe, with sufficient industry, dedication, creativity, innovation, mathematical dexterity, experimental prowess, we take it for granted that we'll figure it out or we'll make progress in figuring it out, because that's what we have found, right? Isaac Newton set us on this trajectory, although there are others before, of course, but at least from the mathematical standpoint, looks out at the heavens and writes down his law of gravity that works up there and down there, writes down his laws of motion. Maxwell and Faraday write down equations and experimental results that describe electromagnetism and radiation and light. And Einstein comes along and starts thinking about all of that and comes up with special relativity, which we then confirm through observations in general relativity. And quantum mechanics comes along, and we're able to understand the microscopic realm where you can do calculations that predict or describe the magnetic properties of electrons to 14, 15 decimal places, and that agrees with experiment. We take it for granted that the universe is comprehensible, but why in the world should it, right? I mean, our brains evolved for one purpose, not to do quantum mechanics, not to do general relativity. Our brains developed so that we could survive in the ancestral world. And why should it be the case that a brain that's fine tuned for surviving in the ancestral environment, getting food and shelter and social interactions, why should that brain also be able to figure out quantum mechanics? Now, there are things that you can suggest for this. We're not a complete loss for this beautiful quality of the universe. Evolutionary psychology gives some insight into these ideas and so forth. But if you ask me, do I find that stunning and beautiful? I do. It's a beautiful fact that this thing called the human brain, inside this cranial structure with the most feeble intrinsic sensations and features that allow us to access the world, has been able to figure out so much about the fundamental workings of reality. That to me is the most amazing thing. Persepolis 8564. Sorry about that. Why is there a speed of light limit? Well, I don't know that there has to be. Somebody earlier asked about the possibility of other universes in which the fundamental constants of nature might be different. And you could imagine there's another universe in which there isn't a speed of light limit. Maybe there's no limit. I mean, Isaac Newton didn't think there was a limit to the speed at which something could travel. So it isn't something that hits you right in the face when you start to think about the nature of reality. Now, in our universe, it does turn out that there is a speed of light limit. And this emerges from Einstein's special relativity. And special relativity appears to work, right? The math and the observations, they agree fantastically. And within that mathematics, you can deduce that there is a limit to the speed that any material object can travel. Any material object that starts off traveling slower than the speed of light can be sped up to near the speed of light. As you do so, the intrinsic heft, the resistance to motion that that object exerts grows larger. And so if you want to go faster and faster, you have to push it harder and harder. And when you get right up near the speed of light, it would require an infinite push to get the object to go any faster still. So concretely, that's why you can't speed an object up to and beyond the speed of light. But did it have to be that way? No. You could imagine a reality where that is not the case. Is it ever possible to conclusively 100% know what is beyond our universe? I won't try to pronounce this name because I will get it wrong. No, we can't, right? The only thing that you can ever know are things that you can directly test or measure. I mean, there are theoretical reasons for anticipating that kind of what we see in our universe is very similar to what we would see if we were at the edge of our observable universe and somehow looking beyond. But, you know, it could be the Truman Show, right? It could be that, we're in this realm. And if you were to break through the edge of our realm, maybe you'd find yourself in a different realm. Now, that is a fanciful idea. There's no reason to take that idea seriously, but is it logically possible? Yeah, absolutely. M411EO, what do you think is the biggest conceptual blind spot in string theory? Is it possible that the framework is so mathematically rich that it's obscuring a simpler underlying idea? Sure. I mean, we've seen it before. I mean, even with things that we understand and understood. I mean, when James Clerk Maxwell wrote down the initial equations of electromagnetism, it was like 20 complex equations that now we can summarize in a very compact form, usually with 4 equations or 1 equation, depending on how powerful the notation that you use. And that's a case where, over time, you find a simplified way of articulating your insights. But could it be that with string theory that we're at an even earlier stage, that we're simply missing the fundamental idea? Yeah, look, if you ask me why that might be, well, look, it can always be the case, but string theory was kind of discovered by accident. Anyone, again, who knows the history knows that it was, way back in the 1960s that people were studying data from particle colliders and noticed a certain property of the data that they surprisingly were able to represent mathematically in a very simple equation. They didn't know why that equation worked, but it did. And then others came along, including, for instance, Lenny Susskind, who I'm going to be doing a live conversation with him in the next few weeks. So watch out for that one. Should be fun. Lenny Susskind looked at that mathematical formula. This is way back in the 1970s. And he said, wait a second, I know what that formula is really describing. It's describing the vibrations of a filament, vibrations of a string theory. And then people studied string theory more and more and found it had remarkable properties well beyond that initial formula that was motivated by data emerging from strong interactions, strong nuclear interactions that were governing the properties of particle collisions at these powerful colliders. And so it sort of fell into our lap, or into Lenny Suskind's lap, from this mathematical articulation of data. And so we've been piecing together the theory ever since. And so could it be that there's a far more potent, powerful, elegant, unique description of these ideas that has a radically different starting point, not the one that we started from accidentally? Sure. And could that reveal things that current ideas have missed? Yeah. Now look, we haven't found that idea, but maybe it's not far away until we will get there. All right. Hello, Dr. Greene. I hope you are doing well. Thank you very much, Elizabeth 8659. I've always heard that time dilation slows time. Is there something that speeds up time? Do gravitational waves do both? Slow and speed up time. So you're right. When you take a course in special relativity, you talk about this idea that a clock that you are looking at that's moving relative to you, time will tick off more slowly on that clock, time dilation. And you also learn that the person who is carrying that clock, they look back at you, and from their perspective, you're the one that's moving in the opposite direction. And they look at your clock and they say that your clock is ticking off time more slowly, time dilation. Again, it's always the slowing of time. Now, let me note two things. Number one, whenever you talk about this idea of time and the relative rate at which it passes, it is always relative, one clock relative to another. So it's never sort of intrinsically that time is slowing or speeding, to get to your question. It's rather relative to another clock. And that becomes all the more important when we graduate from special relativity to general relativity. Because as I mentioned before, if your companion now takes that clock and goes near the edge of a black hole, and you're far from the black hole, their clock will tick off time more slowly because they're experiencing a stronger gravitational pull. Yours is no longer in a symmetric relationship. They can't look at your clock and say your clock is going slow for the same reason, because your environment does not include the black hole, which is far away. And so you will say that their clock goes slow, but they will say that your clock goes fast. So that's the sense. It's not that time is speeding up per se, but relative to the person, say at the black hole, a clock that's far away from the black hole is ticking off time more quickly. And you may have seen this. There are various stories that make use. Even I have a story that makes use of this, a parable called Icarus at the Edge of Time, that they're actually working on a version of that right now. But more in the Hollywood spirit, there's a film called Interstellar, which I suspect many of you have seen. And you may recall that there is a scene in that film where two of the main characters, I think it was Matthew McConaughey and Anne Hathaway, if I remember correctly, They go near a black hole, leaving their mothership further away from the black hole, and they don't spend that much time near the black hole. I don't know, an hour, 4 hours, something like that. Then they come back to the mothership, and their companion, their crewmate, has aged like 23 years because the crewmate's clock has gone fast relative to theirs. That crewmate didn't feel those 23 years fly by. It's not like it was speeding up for the crewmate because everything is time as it always is. It's always the time that you experience, but relative to the clock near the black hole, which is ticking off time slowly, relative to that, the clock on the ship is going fast. And that's why so many more years have gone by on the ship. Okay, what else do we have? What is the difference, Archie BNH asks, between dark matter and antimatter? Well, the difference should be thought of in the following way. For every piece of matter in the world, we believe there is an antimatter partner. So for the electron, which has a negative electric charge, there's a positron, which has positive electric charge. For the proton, there's the antiproton, and so forth. Even for atoms, in principle, you've got hydrogen and antihydrogen made up of the antiparticles. And this is a basic feature that comes out of quantum mechanics, that for every species of particle, there should be an antimatter version of that. And this is true of our understanding of the particles that make up the world. Dark matter is introduced for a very different purpose. Number one, we don't know if dark matter is real. Antimatter, absolutely real. But dark matter was introduced because people who have been studying the motions of galaxies, the way the galaxies rotate and the way clusters of galaxies move, realize that there's not enough matter that we can see in space to account for the amount of gravity required to yield the kind of motion that we see. An analogy that I like to use is if you have a bicycle wheel and it's wet, as it spins, water droplets fly off because there's not enough surface tension to hold the water on the surface of the wheel. Similarly, as a galaxy spins, the galaxies, some of them are spinning so quickly that stars should be flung outward, and yet they're not. And so we hypothesize that there is additional matter that we don't see, hence dark matter, invisible matter, that is supplying the additional gravitational pull that keeps those stars from flying off, much as the water droplets do fly off of the spinning wheel. And so we don't know if dark matter is real. It's an indirect quality that we think should be the best explanation that we have at the moment. There are many candidates that theorists like me have put forward for what the dark matter might be constituted of, the kinds of particles. But you see how the motivation for dark matter is to make sense of certain very specific observations. Antimatter is a general feature that comes out of our theories and has been confirmed by observation. All right. How does bent time make gravity? Moonpie.studio asks. Yeah, I mean, I wish I could give you a deeper explanation than the one that I gave you before. It's basically the fact that when you look at the mathematical equations, the trajectories that objects naturally follow are toward regions of space where time elapses more slowly than it does in the region from which they are originating. Now, you could say, why is that? And frankly, no matter what answer I give you, you could say, well, why that? Why that? And this is the kind of sequence of whys that, we are familiar with from young kids. And it's the scientists who maintain that why urge to have a deeper understanding that pushes the frontiers of science. But according to Albert Einstein, if you posit that this is the description of gravity, you can then make predictions for the external world, and the predictions work. So in the end of the day, our best explanation for why gravity can be described in terms of warped, or as you call it, bent time, is when you do so, you make predictions for the motions of things in the heavens that are borne out to fantastic accuracy. But why is gravity described in terms of warp time? Why is the general theory of relativity the right description of the world? Don't know. Don't know. Okay, how can you tell the age of the universe if time flows at different pace under different conditions within it? If you observe someone, yeah, good. So, yeah, so I made reference to the answer to this earlier, but I'll just be explicit about it now. When we talk about the age of the universe, we're not talking about the age on every single clock that might have been in any environment, undergoing any motion, experience any gravitational field from the beginning of time. No, we are talking about a very specific set of clocks, which are the ones that are in a region that experiences the overall average mass energy influence within the universe. And because the large scale structure of the universe is basically homogeneous, if you're experiencing the average, then you are experiencing that average in exactly the same way here and there and over there and so forth. And it's those clocks moving with the overall flow of the expansion of space and feeling that average amount of mass energy in the universe, those are the clocks on which we talk about the age of the universe. All right, a Facebook question. Given the landscape problem in string theory, what is the most promising route toward obtaining unique, testable, low energy predictions? So Isaac from Facebook asked this question, and you're putting your finger on one of the challenges, but also one of the opportunities within string theory. So look, when I was a graduate student, what was the dream? The dream was that the equations of string theory would predict a unique universe. We would look at those unique properties, compare them to the properties that we measure through experiment and observation. And if there's a match, fantastic. And if there's not a match, it means that string theory is wrong. That was the image. We're far from that image now because clever string theorists and clever mathematicians and clever physicists have studied the mathematics of string theory and found that it doesn't yield, as far as we can tell as of today, a unique universe. It allows for many universes with many different properties. And so it's harder to find observational or experimental signatures when there isn't a unique set of such signatures that emerges from the mathematics. But I have to stress this flexibility that I just described in string theory is not intrinsic to string theory. The standard model of particle physics, which is lauded as the most precise and wondrous creation of fundamental physics, able to describe all of the known particles, predicted the Higgs particle, discovered, and so forth. The fundamental equation or the rubric within which the standard model lives is called quantum field theory. The standard model is a very specific quantum field theory, certain fields and certain interactions between those fields is what defines the standard model. But there are infinitely many different quantum field theories, and there are infinitely many different choices for the interacting strengths between the fields themselves. Even the standard model of particle physics is just one of an infinite number of such formulations that can be written down. So then how does the standard model make predictions? Well, what we do is we use observations to limit the particular quantum field theories that we consider to be relevant to our world. And so we use data to help pick out the specific quantum field theory, and ultimately it drives us to the standard model of particle physics. So the same idea in principle could happen in string theory. Using data, we could be able to limit our focus to very specific incarnations of physics within string theory. Now, that trajectory from the data to constraining the theory is much more difficult in string theory than it is in quantum field theory. And so we haven't made as much progress in doing that. But anybody who tells you that the fundamental problem is that string theory gives rise to all sorts of possible universes. The same is true of the framework of quantum field theory. And so this is not an unfamiliar challenge. It's harder to deal with in string theory, but it's exactly the same kind of issue that you face. So don't be misled into thinking that this is some fundamental failure of string theory. It's a fundamental failure of any theory that we've ever written down. Even Newton's theory of gravity has in it a certain number called G, the universal gravitational constant. It's one particular number, but in principle, theoretically, it could have any value. And we nail down to one through observations that limit the choice of that value. We don't have a theory that comes to us so unique that it simply describes everything in the external world. You don't need to use observation or experiment to winnow down the possibilities. And so the hope is that as we understand string theory better, we'll be able to winnow down the possibilities in a similar way. And at some point, maybe we'll have one string theoretic universe of the many that's able to describe the observations that we make and the experiments that we undertake. Okay, Dr. Greene, as far as we know, general relativity relies on the assumption that space-time, was a long question, space-time is a smooth, continuous manifold, and string theory, Planck scale, physically meaningful. What precise mathematical plays a manifold? Blah, blah, blah. Okay, so the question is, does string theory, which incorporates quantum mechanics, I should say who asked this question, Suraj, another world science scholar, good question, Suraj. String theory, which incorporates quantum mechanics into general relativity, does that change the mathematical way that we think about space-time? Einstein was masterful at going to the math library with guidance, some of his friends, and picking out the right math books written, in the 1800s, the books on so-called differential geometry. And he took those math books and found that the math was exactly what he needed to formulate his general theory of relativity. So he had the math to describe warps and curves in space. That's what differential geometry is. When string theory comes along, does it change that picture? It does. It introduces what we call quantum geometry, right? It's not a particularly creative name, including quantum mechanics to differential geometry called quantum geometry. And we've already over the years found startling new features of quantum geometry relative to the previous classical geometry. Some of the work that I've been involved with over the years, we found, for instance, that the fabric of space can tear apart in string theory and then repair itself in a way that differential geometry would not allow. Einstein would not think it's possible. But in quantum geometry, the string theoretic and quantum mechanical processes allow space to rip and reconnect in a way that fundamentally changes what's known as its topology, its basic foundational shape. And there are many other things that people have found over the years too. So yes, quantum mechanics does change our understanding of geometry. All right, let's see what we got here. If some events, Adam Z5S8D asks, if some events have no definite time order, according to Einstein, how do you think about this, given that time is supposed to order events? It seems like an impossible situation. And Adam Z5S8D, you would be right. It would be an impossible situation if the order of events that are in a causal connected stance were to change. Because we all know that there's something called causality, cause and effect, right? I do something, right? I throw a ball, it hits the wall, and the fact that the ball hit the wall, that was caused by my hand. And therefore, it had better be the case that the throwing of the ball always precedes the ball hitting the wall. And indeed, in special relativity, in general relativity, that kind of causality is preserved. What is not preserved, if two events happen, but they're not causally connected, right? For instance, if I were to snap my fingers simultaneously from my perspective, right? In my frame of reference, my left and my right hand snapped at exactly the same moment. A theorist talking to you, of course, right? But if somebody was moving relative to me in one direction or another, they would come to a different conclusion. They would say that either this thumb snapped or this thumb snapped first. They would not agree on simultaneity. They would change the order of the events. And those two individuals moving in opposite directions would come to a different conclusion regarding which event happened first. Does that mess things up? That's your question. And it doesn't, because these two events are not causally related. It's not that the snapping of my right hand caused the snapping of my left, maybe reversed relative to you, I don't know. It's not the snapping of one finger caused the snapping of the other. They're independent events. And so if two events are not causally connected, their order doesn't matter as much. It's interesting that their order can be changed, but it doesn't mess up the requisite ordering that your question assumed is necessary to have a coherent description of the world. The only ordering that needs to be preserved is the ordering associated with causally connected events. That is the answer to your question. Okay, if one spaceship is going, so at yo boy, yo triple B O Y. Oh, you wanted your handle there to be a palindrome. I get it. If one spaceship is going at 65% the speed of light, another is going in the opposite direction at 65% the speed of light, what would the relative speed of one to the other be? Because it's going to be faster than the speed of light. And you're right, it is faster than the speed of light, right? If I got two of these guys closing in 65% the speed of light, yeah, this distance is shrinking at 130% of the speed of light, faster than the speed of light. You're like, oh my God, what do you mean faster than the speed of light? Well, what Einstein taught us is if you're looking at an object, no object can go through space at a speed faster than the speed of light. But in this case, there is no one object traveling greater than the speed of light. It's simply this concept of the distance between them getting smaller at a rate that's faster than the speed of light. But there's no object that actually is traveling faster than the speed of light. But then you say to me, well, okay, let me jump into the perspective of somebody on this ship here. Then this person would say that this guy is closing in at 130% the speed of light, and that's not the case. That's not the case. When you actually go into one of the ships and look at the other ship, Einstein tells you how to get the speed of that ship. And what you do is normally you'd say, well, I just take, if I'm looking at the situation and this is V1 and this is V2, right? And it's V1 plus V2, you say it's V1 plus V2. But if you jump into this guy's point of view, it's not V1 plus V2. It's V1 plus V2 divided by 1 plus V1 times V2 divided by c squared. That's the relativistic velocity addition formula. And if you look at that formula, V1 plus V2 divided by 1 plus V1 times V2 divided by c squared, that formula ensures that that result is always less than the speed of light. You cut down the V1 plus by V2 by something in the denominator that ensures that the speed is seen by the person in any ship relative to the other ship is always less than the speed of light. Okay, hello from Bolivia. Nask Semler. I would like to know how Albert Einstein's theory of relativity has been applied in the journey of the Artemis II crew. Now, a lot of people I like this. A lot of people want to connect fundamental physics to the Artemis mission, which, by the way, what time is it? Oh, you still got a little time. This splashdown is about 2 hours, 2 hours and change. I don't think I'm going to take you right through to the splashdown. I don't think I can last that long. But the question of, is general relativity playing a role in the Artemis II mission? Not really. It is the fact that when you go up into space and experience gravity that's far less than what we experience here on the surface of the Earth, then time for you will elapse more quickly. It's an example of the black hole scenario. We're like near the gravity, near the black hole, like Matthew McConaughey and Hathaway. And so the ship, which is like their crew member left on the mothership, is experiencing less gravity, at least during part of the journey. And so time will elapse more slowly. And so, yes, they're moving fast, not really near the speed of light, but sort of faster than us. That also affects the passage of time. And so, yes, when the astronauts come back, we could sit down and do a calculation to determine the amount of time that their bodies aged relative to the amount of time that our bodies aged here on Earth. And those numbers will be different, but it'll also be tiny, whatever, a billionth of a second or something like that. I had a conversation with, this the astronaut. Oh my God, someone again can tell me in the chat. His he and his brother, they're twins. Scott, I don't senile moment here. I can't quite figure out. I can't remember the name. But they were the twin brothers. One is in the government. One is astronaut, and they like to joke that because one of them was in space for a certain amount of time relative to the other, then their relative age has shifted compared to the time difference when they were born. But it's all silliness because the effects of relativity, they just don't come into play in situations where there isn't sufficiently strong gravity or speeds near the speed of light. So yes, I wish we could say general relativity is the key to what's going on, but it's really Newtonian gravity that is the dominant thing that is dictating the physics. Okay, what else do we see? Do you see any connection, asks Mr. Hodes 56. Do you see any connection between dark energy, dark matter, and dimensions beyond which we thus far can perceive? That's a really interesting question. I've actually worked on that question. One way of thinking about it is, I mentioned that dark energy is energy that is uniformly suffused through space. Now, if you think about extra dimensions, in fact, let me just give you an example that you can sort of have in mind for extra dimensions. In fact, let me use this cup. Unfortunately, I've got to drain it. So you see how this cup has two dimensions, right? You've got this dimension along the cup, right? And you got this dimension which wraps around the cup, this sort of circular dimension and this long dimension. But now imagine that this cup, the fact that it flares, irrelevant. Imagine this cup is really big, right? And so you have this long linear direction and you have this smaller curled up direction. Now imagine that you also not only make the cup really long, but you make it really skinny. Then you have a situation where at every point along the line, there's a little tiny circle that's wrapped around it, which means if this long dimension is a stand-in for the three dimensions that you and I can perceive with our eyes, because it's big, it's long, we can see it. And if the circular dimension is a stand-in for the extra dimensions, especially if it's really tiny, that we can't perceive because it's so tiny, curled up to such a small size. Notice the following. If you want to have some uniform energy along these dimensions, one way to do it is to ensure that there's some energy embedded within each of the circular dimensions. So if each of the extra dimensions carries energy, that energy will be uniformly distributed along the long dimensions, the dimensions that we inhabit. And so together with a physicist who you may have read some of her wonderful books, Janet Levin, some years ago, I think there was somebody else on the paper too, but I can't recall. Sorry if I'm leaving someone out. We did some calculations that maybe the so-called Casimir energy, which you may recall is the energy just from quantum undulations in space. Maybe the Casimir energy in a curled up dimension spread along a long dimension, maybe that could provide the dark energy that we invoke to explain the accelerated expansion of space. And it's a beautiful idea. I mean, I love that idea. I mean, how economical to start with a theory that has extra dimensions. And as you know, string theory requires it. There are other approaches. Kaluza-Klein theory requires it. And if the dark energy were a natural consequence of extra dimensions, that's a beautiful coming together, exactly as the questioner asked. When we did the calculations, it's not impossible for this idea to work, but it's pretty unnatural. It's very hard to get the right amount of dark energy. It's very hard to stabilize the extra dimensions so they themselves don't start to grow or contract. So it's the execution of the idea that makes it hard to really have any confidence that it's the right way to go. But it's a beautiful suggestion from the audience that yes, there could in principle be a connection between dark energy and the extra dark dimensions. Now, this is a different cup of water. But yes, I like that idea a lot. Okay, so um, if energy cannot be created or destroyed, asks Pendremo, if energy can't be created or destroyed, where does the energy in a photon go when it's cosmologically redshifted, right? So we often, that's a beautiful question, right? So we talk about redshift, right? I discussed it earlier in connection to black holes, right? We said that black holes emit Hawking radiation. These photons, which are little particles of light, they travel away from the black hole and they get redshifted. They get redshifted because they're fighting against the gravity of the black hole. When they fight against the gravity, their wavelengths get stretched out. Also, there's cosmological redshift as the universe stretches, right? Also, photons get spread out, their wavelength gets larger, pushed more toward the red. Now, energy, according to quantum mechanics, is something that is inversely proportional to wavelength. You may recall this famous formula that Max Planck wrote down in 1900. E equal h nu. H is Planck's constant, nu is frequency. Frequency is basically the inverse of wavelength, c, speed of light divided by wavelength. So, bottom line, as the questioner rightly asks, if wavelength gets larger, energy gets smaller. Where's the energy gone? The questioner rightly asks. Have we lost the energy of the photon? And we don't believe we have lost the energy for the photon. The answer is basically the same answer to the following analogous question. If I have a baseball and I throw it up into the air, the baseball goes slower and slower and slower, which means its kinetic energy is getting smaller and smaller and smaller. Where does the energy go? The kinetic energy is getting smaller. Now, any high school physics student knows the answer to that. It's not that the energy is lost. The kinetic energy is not lost. Instead, it gets turned into gravitational potential energy, right? So the full energy of the baseball is kinetic plus potential, and kinetic goes down, potential goes up as the ball is going higher and higher upwards. Similarly, as a photon is going further and further from a black hole, let's replace the Earth with a black hole. As the photon is going up, yes, its energy from its wavelength is getting smaller, but that's going into, we believe, the potential energy. Again, the gravitational potential energy, because it is the gravity of the black hole that is pulling on the photon, causing the wavelength to stretch, just as gravity is pulling on the baseball. So it's actually the same basic idea. It's the energy interchange between different kinds of energy associated with the photon itself and the associated energy for gravity itself. Okay, what else do we have here? Um, if I, oh, here's one from at JT009GV. Wow, very creative names. In the framework of infinite scenarios in the universe, does a single scenario repeat itself infinitely many times? And would that be considered the same scenario or different scenarios that are yet identical? So, what the questioner is asking is, if space goes on infinitely far, there's a beautiful theorem you can pretty much prove using the most basic qualities of physics and mathematics that the reality that we inhabit has to be out there someplace repeated. Yeah, I mean, how can you prove something like that? Here, let me just give you the basic proof. It's so straightforward. So, in any finite region of space, it's not hard to prove using basic physics and basic quantum mechanics, and it's not unreasonable even just to intuit it, that there are only finitely many different arrangements of the particles in that region. Finitely many different places that they could be and speeds that they could have. You do need some quantum mechanics to really establish that fact. But let's take that fact as a given. Any finite region, finite arrangement of particles. Now, if space goes on infinitely far, and let's assumption that there are particles pretty much uniformly spread throughout this large infinite expanse. Well, in every region of that infinite expanse that's roughly the size of our region, there are also only finitely many arrangements of the particles. If space goes on infinitely far, they can't all be different, only finitely many arrangements. space goes on infinitely far, there are infinitely many chunks the size of ours. It's sort of like the analogy I love to use is start with a deck of cards, right? The deck of cards is some particular order, right? You start to shuffle the deck, you get a new order, shuffle again, a new order. Sooner or later, you've got to get the same order because there are only finitely many different orders of the cards in the deck. And if you shuffle the cards infinitely many times or more than the number of distinct configurations of the cards, you have to get a repeat. Similarly, you've got to get a repeat of the particle configuration that is holding in our realm. Now, if the particle configuration repeats, that means reality as we know it repeats. I am a collection of particles in some arrangement, as are you, as is everything in the world around us. And if the particle arrangement repeats, then you repeat, then I repeat, and so forth. In fact, it's even easier to have a near miss, an almost complete identical repeat, right? That's like shuffling the cards and almost getting the identical order with which you began. It's easier, right? So it's even easier that there are realities out there that are similar to ours, but not exactly identical. So the questioner is asking if there are these other copies of us out there, and truly, if space goes on infinitely far, there'll be infinitely many copies. They'll be widely spread out, but they have to be there. Are those different realities? And I think they are. I think they are different realities, right? Because they are located in a different realm of the world, a different realm of reality. They're far away from us. And so it's a mind-bogglingly strange idea, but it's one that naturally emerges. Now, look, there are a bunch of assumptions. I assume that space goes on infinitely far. Maybe it doesn't. I assume that particles are pretty much spread out and it's the same particles spread. Maybe physics changes out there and there are different species of particles, or maybe there's nothing. Maybe you go out of our realm and you go sufficiently far and there's nothing out there. It's total darkness, total blackness. Is that possible? Yeah, that's possible too. But under the mild assumptions that space goes on infinitely far, there's no boundary, no edge, it doesn't sort of curl back on itself like the surface of the earth, and there are particles out there, that is where we go, which is a strange, strange conclusion. Okay, what else do we have here? Let's see. Oh goodness. If we can never see an object fall into a black hole, asks Waiting for Godot. Perfect question for at Waiting for Godot. Or Waiting for Gödel. I'm sorry, I thought it was Waiting for Godot. That would have been perfect. Waiting for Gödel, that's sort of good, but it's a little bit different flavor. If we can never see an object fall into a black hole, does that mean that when we see the black holes today, we see them at the size they were when they first formed? Holy smokes, this is a great question. This is a tough question. I'm not sure how far to go with this question, but I'll give it a shot. So you're absolutely right. When you have a black hole, right, naively, we say that the size of the black hole is dependent upon how much matter fell in when the black hole was created. In fact, there is this formula, I gave it earlier, that the radius of the black hole is proportional to its mass. So if more mass falls into the black hole, you'd say the black hole should get bigger, right? Because of the exact same reasoning. On the other hand, I also said to you that when something falls toward a black hole, it goes slower and slower because time slows down. And indeed, if you follow this in more detail, the object gets kind of spread around the edge of the black hole. And as it gets right to the event horizon of the black hole, according to the equations, the object freezes. It stops. Slower, 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 stops right at the edge. So you never actually see it go over the edge. So if you never see it go over the edge, do you ever see the black hole get any bigger? Oh, now we're in an interesting place here. How does this work? Well, there's this long-standing confusion and insight and revelation about black holes. A lot of it was due to Roger Penrose, who really helped us to think about black holes. When you talk about black holes, you're really talking about the entirety of space-time, not all of space, but all of space-time. That includes the far future. And so when you have a black hole solution, the location of the event horizon really depends upon the far future. Why is that? Well, because the very definition of the event horizon is the location from which light cannot travel to spatial infinity given infinite amount of time. So you need to know the trajectory of light beams infinitely far into the future to really even talk about the event horizon of a black hole, which means, weirdly enough, when you study this in more detail, if you have a star or a spherical cloud of matter that's collapsing into a black hole, the event horizon of the black hole, it doesn't just suddenly form when the matter is sufficiently close in. The event horizon actually begins to form as the matter is falling inward, and it kind of expands out to meet the infalling matter. And so some people use the language teleology, that somehow the space-time of a black hole knows about the far, far future. And that makes sense because, as I mentioned, the definition of the event horizon, the edge of a black hole, you define it in terms of the far, far future. And so, to really answer your question, you have to note that as matter is falling in, the horizon is already accommodating that matter, assuming that the matter does make it to the black hole and thereby affects the trajectory of light beams infinitely far into the future. I don't think I should probably go any further than this. This is deep and wondrous stuff, but you can find this discussed, in the textbooks in general relativity. And so wonderfully confusing and rich fact that black holes, at least in their pristine description, know about the entirety of space and time. All right, what have we got coming up here? Do the equations of string theory have a component that describes its impact on the passage of time similar to general relativity? And at Joseph Powers 117625, and the answer is absolutely yes. And this is really one of the claims to fame of string theory. I mentioned, I don't know at Joseph Powell if you've been with us for the entire session, but I mentioned very briefly early on that string theory was discovered by accident. People studying data from particle colliders, and from that data guessed a formula, which then people realized described the motion of a vibrating string. Subsequent analysis of the equations of string theory revealed, staring us in the face, Einstein's equations of general relativity. You don't put general relativity into string theory. General relativity emerges from the motion of a vibrating string. That is amazing. And that's wondrous and that's beautiful. And I hope that gives you, I don't know, one of those like chills or tingles up your spine, right? Albert Einstein spent 10 long years between roughly 1905 and 1915 carefully developing the mathematics of general relativity, right? String theory, starting from something that has nothing to do with gravity, describes data at these particle colliders, develop the mathematics, and then within the math, you see the equation that Einstein presented to the Prussian Academy on November 25th of 1915. It emerges. When you see something like that as a theorist, that's a once in a lifetime moment. I'm serious now. I mean, people wonder why we have gotten so excited about string theory and why we've stayed with it. Just join me in thinking about what I just described. The greatest thinker, at least scientifically speaking, that our species has ever produced, Albert Einstein, spends 10 years and comes to the equations of general relativity, right? Say it with me. R mu nu minus a half G mu nu R equals 8 pi G C T mu nu over C to the fourth, right? That equation then emerges unbidden from the equations of string theory. And you're like, wow. And so, of course, then the answer to your question is, yeah, anything that general relativity predicts, string theory predicts. because the equations of general relativity emerge from string theory. In fact, more than that, the equations of string theory include corrections to Einstein's equations that only really come into play in the most extreme of environments. In fact, I had a high school student years ago. In fact, just coincidentally, like 2 or 3 months ago, I was entering the lobby of my building here in New York, and she was coming out of the elevator because she had been subletting an apartment in the building. It was wonderful. I hadn't seen her in whatever, 15, 20 years. But she was about the smartest high school kid I've ever encountered. I think she may have gone to Stuyvesant High School. I'm not going to give her a name. Don't want to embarrass her. But she did a calculation with me for a high school science project. I forget exactly what it was for, where she calculated the corrections to the bending of starlight, which is the key triumph of general relativity. But the new term that string theory gives, the corrections to Einstein's equation, give a correction to that bending, and she calculated that bending. Of course, it's tiny. I don't remember the answer, but probably like 1 part in 10 to the 90th or something, not something that you're ever going to observe, but it's just so beautiful. String theory gives Einstein's equations plus new corrections that allow you to update the very predictions that Einstein put forward to test the general theory of relativity. I mean, as they say, you can't make this stuff up. You can't write this stuff. And it makes you feel that the universe is telling you something when this kind of a development takes place. So yeah, that's where the excitement comes from. If you could design one experiment, MoonPie Studio asks, with unlimited budget, unlimited technology, but it has to be physically possible to resolve the deepest open question in fundamental physics, what would it be? Well, look, I mean, since we're talking about string theory, I'll stay there. In principle, if you had a large enough collider, and you're kind of giving me infinite leeway as long as I'm not contradicting some fundamental law of physics. If you have a large enough collider, you could have arbitrarily high energies. Yeah, I mean, I guess you're going to start to create black holes. And yeah, look, don't hold me to all the details here. But if you had a sufficiently powerful collider and you were able to collide particles with energies near the so-called Planck energy, you should begin to see the effects of string theory. So if you want to answer whether string theory is the right description, yeah, an arbitrarily large particle collider would certainly be one way of going about it. So it's just to say, when people say that string theory is not testable, what they really mean is that string theory is not testable with any kind of practical piece of equipment, with a practical budget, or with a machine that we could build with today's technology and so forth. But a question such as was just asked, if you take away practicality and allow just the laws of physics to be the only delimiting factor in what you can actually do, then yeah, string theory would be a testable theory. Dr. Greene, we know from Bekenstein and Hawking that black hole entropy is proportional to its event horizon area. Okay, going pretty deep here. The question is, let me find it. I've lost it. Establishing a deep link between gravity and thermodynamics. In string theory, you have extra dimensions. Do the microstates of the extra hidden dimensions contribute to the entropy of black holes? And yeah, that's a great question too, right? What Stephen Hawking did back in 1974 was to answer a puzzle that really originated maybe with John Wheeler, and as indicated in the question, his graduate student, Jacob Bekenstein. Here was the question that John Wheeler asked. John Wheeler was this, I mean, I had, unfortunately he's passed on, but I had lunch with John Wheeler when I was writing my first book, The Elegant Universe. It was just so amazing. He's the poet philosopher of physics. He can do the mathematics, but he has this way of coming up with seemingly simple thought experiments that wind up revolutionizing our understanding. So here's a thought experiment that he came up with back in the 1970s. He says, look, here's this black hole solution that comes out of Einstein's equations. Things fall into a black hole. They're kind of gone. That was the lore at the time. So he said, how does this comport with the second law of thermodynamics, which says that entropy is always on the rise? Entropy can't go down. He said, look, what if I have a cup of tea? The genteel Professor Wheeler said, the hot water in the hot cup of tea has a lot of entropy, a lot of disorder. What if I throw my cup of tea, he said, into the black hole? The disorder seems to go away. It's gone, never to come back. Have I thereby decreased the entropy in a way that conflicts with the second law of thermodynamics? He asked this question to Jacob Bekenstein. Bekenstein comes back, I don't know, weeks, months later and says, no, you haven't lost the entropy. The entropy went into the black hole and the black hole responds. The black hole's event horizon changes in response to the entropy that went inside. And so if you include the entropy of the black hole and the entropy of the cup of tea, their total doesn't go down. Sure, the outside entropy goes down, but the inside entropy compensates. That was the basic idea. Stephen Hawking then looked at this and got the radiation that we're talking about. But the question that's being asked is, what if you do the same thought experiment in string theory? In string theory, you've got these extra dimensions. Do the extra dimensions themselves have the capacity to hold on to entropy? And the answer is yes, absolutely. In principle, yes. And in fact, you can imagine that the extra dimensions are bigger, in which case the black hole is no longer in 4 dimensions. It's really in 5 space-time dimensions, four space and 1 of time. And people can write down the black hole solution in 5 dimensions. And in fact, Strominger and Vaffa used black hole solution in 5 dimensions to gain insight into the microstates of black holes. It's a whole nother story. But the point is, if those extra dimensions are big enough, then they can hold on to entropy, and the entropy has to take into account the area, the volume associated with the extra dimensions themselves. If you make the extra dimensions smaller and smaller, then it's harder and harder to excite fluctuations, degrees of freedom in the extra dimensions. So the smaller you make those dimensions, the higher the temperature, the higher the energy you need to actually to excite those degrees of freedom. So in that sense, they kind of decouple in the limit that the extra dimensions are brought down to the Planck scale. But in principle, yeah, the extra dimensions are there. Extra dimensions do hold on to entropy. Okay. I was hoping to ask one of our questioners about superluminal propagation. I remembered learning from your work that this might be possible. How does this work? Yeah, this is Evie Elgart who asked this question. And Evie, you're right. I wrote a paper a couple years ago. The results surprised me, which showed that there are certain geometrical contexts in which you can have a light beam travel from one point to another at a speed that is faster than the speed of light. You say, but wait, if it's a light beam, how's it faster than the speed of light? Well, let me give you another example over here. I wish I had a pen handy. I should have brought one. It doesn't matter. But imagine that you live in this dimension. This one dimension now is the 3 dimensions that we live in. If you want to send a light beam from here to here, how do you do it? Well, the simplest thing is just send the light beam from here to here. But you can also send the light beam in a more exotic trajectory, if you think about it. A light beam that kind of circles around the extra dimension and gets here that seems like the long way. So you'd think this is the short way and this is the long way. And therefore you'd say this signal should get there first. This signal should get there second. It turns out that this signal that we're talking about here, in certain circumstances, can get there first, not second. It does require that you have certain ingredients from string theory, like a membrane on which we live that's itself moving in these curled up extra dimensions. But modulo those details, we were able to show that in those circumstances, the beam of light that goes this way gets there before this one, which means that this signal is going faster than the speed of light according to observers in our 3-dimensional universe. And in fact, we found that the signal, this is crazy, the signal can get to this location before it was actually emitted. It can actually go back in time, go back in time. Now, you might say, okay, now Professor Green's off his noggin. He's talking nonsense, right? You're going to ruin causality. The basic ideas of relativity are being violated, but they're actually not. So what we found is you can send a signal, get it here before it was emitted, but then you say, what about that person? Can they send a signal back? They can, but it will always get here a little after it was emitted. So there's no undermining physics in terms of being able to sort of shoot the person before they send the light beam. So how was the light beam ever sent out in the first place? So all those time travel paradoxes that you may be familiar with from, Back to the Future or just from your own readings, all resolved in this circumstance. But in a universe that has curled up dimensions, you can send signals in a manner that apparently is faster than the speed of light. All right. Anything left in our list of questions? If space has energy and the universe is accelerating, doesn't this violate the conservation of energy? And this is Douglas W. Lip Channel 5546. No, well, first of all, I have to disabuse you guys of one thing. In any region of space, there is a notion of conservation of energy. And it's the one that basically you learned in high school. Some of you learned about conservation of mass. It's unfortunate if the instructor didn't go on to conservation of energy. But anyway, you've at least encountered the idea that in a laboratory environment, there's conservation of energy. When it comes to the entirety of the universe, there actually isn't necessarily a conservation law globally that tells us that globally the total amount of energy always is fixed, only locally. And so you shouldn't get bent out of shape if there's a situation in which there isn't global conservation of energy. Now, locally, the way we describe it is, yeah, when the universe is expanding, it's again much like the baseball analogy I gave earlier. That was for a black hole, but you can apply it cosmologically. As things move further apart, right, there's energy that's pushing them apart. So you say, well, isn't energy being expended? It's going down. Well, no, it's going into the gravitational energy. Gravity is what is facilitating the expansion of the universe, and gravity itself has energy. And so, again, it's the interplay between the two that allows you to avoid any local violations of conservation of energy. Greetings, Dr. Greene. Imagine if an observer is looking at our universe from outside. Would it be like a vibrating jelly due to gravitational waves? Well, not even have to be looking from the outside, right? We have gravitational wave detectors within our universe. And as you all know, we've detected ripples in the fabric of space. Now, we've only detected them from specific astrophysical events, right? We've detected them from neutron stars rotating and slamming into each other, black holes similarly rotating around each other and slamming into each other, giving rise to ripples in the fabric of space. What we've not yet detected are, for instance, ripples in the fabric of space from the Big Bang, the entirety of the universe undergoing this rapid expansion, causing the fabric of space uniformly to have this jittery, vibrating quality coming from the disturbance of the Big Bang expansion itself. We hope that we will detect that from inside our universe. That would be absolutely wondrous. Like one possibility is, this LISA experiment, the laser interferometer space antenna that, I don't know, people say in the 2030s, maybe it'll be out there, these 3 satellites forming whatever, probably an equilateral triangle, I assume the shape will be. And the satellites will be able to monitor their relative separation. So if a gravitational wave goes by and causes 2 to go together or other 2 to separate, those small differences will be detectable. that device may be able to detect ripples in the fabric of space coming from the Big Bang. And so, yeah, a jelly-like phenomenon suffusing space coming from this primordial creation event. Yeah, you don't need to be standing on the outside. At Pawan Pandy W4, if an atom is 99% empty and we are made up of atoms, then are we empty? Well, let me give two answers. One is, yeah, in this image, that, very classical image of an electron sort of orbiting around the nucleus, and there's basically empty space is the dominant quality of the atom, then yeah, we're made of those stuff. So we would be mostly empty space too. The only thing I want to caution you on is that classical picture can be misleading. Most of us who are steeped in quantum physics, we tend to not think of the electron as this little planet orbiting the nucleus, the sun. Rather, we tend to think of the electron described as this probability mist, this wave function. And that probability wave fills the space. And so if you use that picture, it's not as empty as the classical image might lead you to suspect. So basically, atoms are this electron probability cloud that really extends throughout the environment. It's denser in locations where the electron is more probable. It's more suffuse in regions where the electron is less likely to be found. But in that sense, quantum mechanics kind of updates that very classical picture. Hi, Dr. Greene. Will you be tuning in to the Artemis return on Earth? This is our nearest neighbor. Do you think we'll ever visit the other planets? Antimony, yeah, Antimony, you probably weren't here at the outset. We started with a little quick rundown of what the Artemis mission has accomplished. And indeed, the splashdown is happening. I don't know. I would look at my phone, but I have an incoming call, which is taken off the phone number. It's probably still a couple hours from now, I think. So, no, I'm unlikely myself in this live stream to turn to that. In fact, I'm just wondering, since someone just asked, can we bring up the live feed from NASA? I mean, what do we got going on here? So this is the live feed at the moment. It just looks like one of the still images, but they don't have anything in the Artemis craft itself, I guess, at the moment. So I don't know exactly what that is telling us, but yeah, so not much interesting happening in the NASA feed, so we can sort of take that off and go back to ours. But yeah, those of you who are interested, 8:07 Eastern time is when the splashdown will happen. And look, we've all got our fingers crossed. I don't know if you all saw this article in the New York Times. I mean, I have not been diligently following Artemis the way perhaps I should have, but an interesting article today raised some questions about the heat shield. Artemis 1, apparently, when they examined the heat shield, which was what protects this entry capsule, it kind of had more damage to it than they would have anticipated. But nevertheless, it still protected the capsule. But it does, I don't know, raises some questions, especially after the disasters that have happened in the past. But at least the article has a number of NASA scientists saying that the margin of error is so enormous here that even if they're not in command of all the details of the material response to the fantastically high temperatures on reentry, that there isn't any danger. So we hope they're right. We hope that they are absolutely right. Okay. What do we got here? So if measurements of space and time vary, we're asked, between observers, how do the laws of physics remain consistent and universal across all frames of reference? Yeah, this is a great follow-on to a question that was asked earlier, which is, if the orders of events can change, how do we maintain a consistent description of the universe? This is more general. If the observations of people in relative motion really differ in terms of what happened and why it happened and where it happened and when it happened, how do you have a universal physics? And the beautiful thing is that relativity does not make everything relative. It makes relative things that we thought were not relative, right? According to Newton, duration, not relative. You and I always will agree on how long it takes for something to happen, right? Um, the the total energy in a situation is something that we can differ on, but there's a certain combination of energy and momentum. E squared minus p squared is a combination of things that previously we thought were invariant that itself remains invariant, even though the pieces that we thought were unchanging do change. And so these are the kinds of things, right? I mean, there's an invariant interval. If you take delta t squared minus delta x squared, any observer in the world, regardless of their state of motion, will agree with any other observer on the world in the square of the duration minus the square of the spatial separation between events. And so it's not that everything becomes relative. It's that the things that we thought were invariant are not, but there are new invariants that come in and replace them. And those are the things that we can absolutely agree on. All right. Anything else before we wrap this up? I seem to recall some interesting questions about AI that, yeah. So there's a question that someone asked earlier, no longer on my list, about how is AI going to affect physics research? And bottom line is, I don't know, but I will say that there's a real possibility, and there are people, serious people in the field who I've heard say things like, we've got 5 years left as theoretical physicists to really make our mark, because 5 years from now, the AI systems will be so powerful that they will be taking the lead in much of what we do. Do I really believe that? I'm not 100% sure I do, but I'll give you one small story. I was working on a paper not that long ago with a handful of colleagues, and we took a while to get this result. You can look up this paper. It has to do with unorientable manifolds as compactifications. I'm only giving the details because it's a really esoteric subject that involves mathematics that even many cutting-edge physicists have never needed, therefore they don't know it. And so it took us a while to work this stuff out. I then, after we had the result, wondered how long it would take Chat, viewed as a graduate student, to get the results. So I had a conversation with Chat, and I really treated it like a graduate student, not giving the answer, right? You don't give the answer to a graduate student. The whole point is that you guide the student toward a direction of research, and you hope that they're able to push forward and get an interesting result. And that's really what I did. A few pointers, a few suggestions, and within a half an hour, Chat had the entire answer. And I was like, wow, I've never encountered a graduate student who could do that. And it's obvious why. It would take the graduate student a couple months just to learn the necessary background mathematics to be able to do the calculation. But Chat doesn't need any time to learn anything because it knows everything. It's read everything. It knows every math textbook that's been on the internet. And so it's incredibly powerful even today, at least at the level of a graduate student. A friend of mine, Mike Douglas, revered string theorist researcher, he described it. He said, basically, every physicist today has sort of an army of 100 or 1,000 of the best graduate students you could imagine at their disposal. And I think that's a reasonable summary. Now, it isn't the case right now that AI can make that creative leap, that unexpected leap that we like to think is really us, that no mechanical digital system is ever going to be able to do, that moment of inspiration, that allows us to do something that no one's ever done before. But I have to tell you, a lot of those moments of inspiration, what they really are is putting together things that are not usually put together, novel combinations of things that are known, but brought into a novel context, right? I mean, again, Einstein's general relativity, the math was known, right? It was putting it into a very different context. Even special relativity, the basic math was known, and it really emerged from studying Maxwell's equations and understanding their symmetries in a deeper way than anybody had previously done. And so a leap of insight is not necessarily creating something from scratch. A leap of insight can be putting together novel qualities, or I should say, putting together existing qualities in a novel pattern, a novel way. And that's the kind of thing that these systems, are pretty good at. And if these systems get 1,000 times more powerful, 10,000 times more powerful, I was having some conversation in one of our interviews, I think it was with Eric Schmidt, who said, you know, 10,000 times more powerful AI in a reasonable span of time is absolutely expected. And so special purpose AI systems that know all physics research, all physics data, all astronomical research, all astronomical data. Can I imagine that at some point they take the lead in pushing the frontiers of scientific understanding? Yeah. And we'll just have to see where that goes. And again, it comes back to my earlier prognostication. Maybe it's really a union, not us versus them, not us saying, hey, you're stepping in our lane, you're stepping in our turf, you're moving in my lane. No, no, maybe it's, hey, let's really get together. And that's is what happening. The NSF, I believe now, or DOE, they may have both, are having special grants for those that are bringing AI into fundamental research. Many of the big companies are pushing into fundamental research. So yeah, I think that may well be where the future goes. All right, I'm getting a little exhausted. I don't know how you guys are doing, but I think it's time that we wrap this up. You should. Thanks for joining us, and stay tuned. I've got some interesting conversations in the next few weeks. Sean Carroll, we're going to talk to, Lenny Susskind. Uh, I think we're going to talk to Nick Bostrom in the not too distant future, and so forth. So these will be fun conversations coming up. So subscribe to our YouTube channel if you aren't already, so you can be alerted to those. And again, at 8:07, let's watch the safe return to Earth of 4 courageous astronauts who have gone further than any human has gone before. Thank you so much for joining us.